Welcome back to the final video of Unit 5, which covers sampling distributions. We've devoted almost this entire unit to setting up how to determine what models we can use for different situations when we need sampling distributions. And how we're going to use these distributions isn't quite clear yet. I'll just tell you for now what we're going to be talking about for the rest of the course in all the later units uses the idea of sampling distributions as a base. We're going to be using these models going forward. So I don't want you to think that this is some isolated concept that once we're done with it, we're just not going to talk about it ever again. This provides the basis for what we're going to be doing in the future, which is our ultimate goal of being able to say something about a population based on a sample. We need to know how the samples within a population behave before we can do that, and how to describe how samples from a population behave is the entire point of sampling distributions. We've covered how to determine how these samples vary for sample proportions for one population and for the difference between two populations. We've done the same thing for means. How do samples of a given size vary within a population for a sample mean? We've done that for one distribution at a time, and we did that for both of these sample means. The only thing left is to put two sample mean sampling distributions together, and that's what this video is about. So, we've already established at length in that last video that we can use these models for the sampling distributions of the AP test sample means. For the stats AP test, the sample means follow a normal distribution because we check the conditions. It has the sampling distribution of the sample means has a mean of 2.88 and a standard deviation of 0.194. And remember, for the stats test, we're taking samples of size 50 for that sampling distribution. And for calculus, again, a normal distribution, we met the conditions, and it has a mean of 3.8 and a standard deviation of 0.143, and we took samples of size 100 for that test. So the only thing we're left to be interested in is how can we model the sampling distribution of the difference between those sample means? Well, we start by checking conditions, and these conditions are going to be very familiar to us. The first condition we need to check should be pretty familiar. We've checked it before for every other sampling distribution. And we need to make sure that the individuals within each population are independent of each other. And since we've got two populations here, two sampling distributions representing a population each, we need to check that independence condition for each population separately. So how do we do that? The 10% condition. As long as we're sampling less than 10% of each of these populations, and remember the populations here are students, all the students who took those tests, then we're good. We're sampling way less than 10% of all the students who took these tests. We're only sampling 50 AP Stats students and 100 Calc 2 students. So this condition would be met. The next one, since we have two populations here, there is a condition that we need to check that we didn't need to when we were only looking at one population at a time. And these populations need to be independent of each other. This is the one condition of all the sampling distributions where it's acceptable to assume that this condition is met, or to kind of hand wave and just say it is, unless there's some serious concern. And in this particular context, yes, some of the students that take the AP Stats exam and are in that group also took the Calc 2 exam and were in that group. So technically, to the letter of the law, those groups are not independent of each other. However, there were a lot of students that took those tests, and I don't think that the fact that some students are in both populations would necessarily mean that these groups aren't independent, because how a student does on one test could be entirely different than how they do on the other one. Maybe they got a 5 on the AP Stats test, but got like a 2 on the Calc 2 exam because I don't know why, right? So even if you think there might be some issues with this condition, generally unless you're being really pushed towards the fact that there's something really connecting these two groups together, you can just say this condition is met. This should never really be the reason that you failed to use the model that we're going to talk about here. The last condition we need to check is, again, common to every sampling distribution, in theory. The fact that your samples have to be large enough to use the normal model, which, spoiler, is what we're going to want to use here. Now, this is the condition that is different depending on whether your sampling distributions are about sample proportions or sample means. For sample proportions, remember we had n times p and n times 1 minus p being at least 10. If you're looking at sampling distributions of sample means, or the difference between two like we're doing here, it's the fact that these sample sizes need to be at least 30. And when we introduced this in the last video, we said that's more of a rule of thumb. If your populations that these sampling distributions are coming from are already normal or approximately normal in shape, the sample sizes don't even have to be at least 30. They could be of any size, and this condition's met. But if you're given something like this, the population distribution is super skewed or has some really extreme outliers, you may need sample sizes bigger than 30 even. Like, it may need to be even more than that. But again, as long as you're not given some serious evidence to the fact that this condition's not met, you should provide that evidence, cite your sample sizes. This one's 50, this one's 100, and explain how that means that condition is met. So, these are the conditions that you need to check whenever you're taking the sampling distribution for a difference between sample means. And we check these conditions for this specific scenario, but in terms of building the model, I want to show you what it looks like in general first, and then we'll talk about what the model looks like for this particular example. So in general, if all these conditions are met, then the sampling distribution of the difference between two sample means, x bar 1 and x bar 2, is going to have a normal model. That's what the large enough samples allows us to do. This is using the central limit theorem again. We're going to have a normal model. The mean of this sampling distribution, which is going to have this notation, it's the population mean for the difference between the sample means, is just the difference between the population means. It's that simple. Sometimes I wish things were a little more difficult so it would look more impressive, but really, that's it. And that's exactly what you would expect. Again, the population means for these sampling distributions act like you would expect. For the difference between two sample means, the mean of that sampling distribution is the difference between the population means. The standard deviation for that sampling distribution is going to be equal to, I want to make sure I write this correctly, it's going to be the square root of the variance of the first random variable, which is going to be the variance of x bar 1, or no, sorry. This is just the variance of the population for the first population divided by the sample size, plus the same thing for the second one. Right. So each of these terms separately is the variance for the first variable here. So this is the variance for x bar 1, this is the variance for x bar 2, and when we combine those random variables, we add the variances, always, and then take the square root to get the standard deviation. So that's the formula in general. This would be a good time, if you want to pause the video for a second, and determine what these parameters are for these two when we combine them this way. We want to take the sampling distribution of x bar c, so x bar calculus, minus x bar for statistics. So if you want to calculate those parameters on your own and then check your work pretty quick, pause the video, come back when you're done, and we'll see how you did. So this is what I ended up with. For the mean of the sampling distribution, for the difference of the sample means, you just subtract the population means, which just so happen to be the same as the means of the individual sampling distributions. So we're taking 3.80 the mean for the calculus, minus 2.88, the mean for the statistics. Now, for the standard deviation, you may have gotten something different here. And if you were using these numbers, I can understand why. Now, there are two ways of going about this. If you want to use this formula as it is, these variances are the variances of the original populations, not the sampling distributions. So I kind of faked you out there, and I'm sorry about that. If you're going to use this formula with these population variances, those population variances, or the standard deviations, were these numbers. So you would have to put, I put 1s and 2s here instead of C's and S's. So if you're using this formula, the numbers that would go there are actually the population variances. So that would be 1.43, which is the population standard deviation squared, divided by the sample size for calculus, which was 100. And then up here would be the 1.37, which is the standard deviation from the stats population squared, divided by 50. Now, I kind of faked you out. I didn't put the right numbers there, so I apologize. You should have used this formula, and now you know that those are the numbers that go there. Now, what I've written here is essentially the standard deviations of these sampling distributions. Remember, this formula is just the square root of the sum of the variances. So this represents the variance of the sampling distribution for calculus. And this was the standard deviation. So if we just square this number, that's the variance for the calculus sampling distribution. We can do the same thing for stats. We square the standard deviation to get the variance. But if we're going to use the standard deviations for the sampling distributions, we don't need to divide by n, because these numbers, we've already done that. Okay, so you're essentially redoing your calculations if you use this formula. You're redoing what you already did to get these. Okay, and if you want to use this formula and you want to redo those calculations again, please, by all means, do that. If you're someone that's looking for shortcuts all the time, if you've already calculated these for the sampling distributions, you can just square them in here because you're just taking the square root of the sum of the variances. Either way, this one or this one, you get 0.241. Okay, so I'm sorry I made that so complicated. I apologize for not giving you the right standard deviations here for this formula, but I hope that it's a little more clear now. If not, let me know, shoot me an email, and I'll explain it again or give you different values that you can do it fresh once again. I want to make sure that we can calculate these parameters, but also that we can understand what they mean. And again, I think that the trickiest interpretations for these sampling distributions are when we start combining the random variables, or we're taking two populations. So let's start with this mean here. We got 0.92 here. And I want you to look at this notation to try and understand what this is doing. We are taking the population mean of the difference in sample means between these populations. We are doing the average difference between a sample mean for calculus test scores and a sample mean for statistics test scores. Okay, the word mean is flying around all over the place and it can get really confusing. But here's the interpretation of this value. For all possible random samples of 100 AP Calc BC scores, right, we took 100 Calc scores at a time, and 50 AP Statistics scores here. The sample mean of the calculus scores is greater than the sample mean of the AP Stats scores by 0.92 points on average. The average, you could also say the average difference between those sample means is 0.92 points. I went one step further here, and you could just say the difference is 0.92, but in fact, since you're taking calculus minus statistics, and that difference is positive, it means this sample mean, on average, is greater than this sample mean by that much, on average. Okay, so there is your interpretation for the mean of a sampling distribution for the difference of sample means. Interpreting these parameters, especially for some of these sampling distributions, can be tricky. My strategy for interpreting these parameters is to think about what does the parameter do in general, and then what is the random variable that you're trying to interpret it for. So, what do standard deviations do in general? They show you how much the values in a data set typically vary from the mean. That's what a standard deviation does in general. What are we trying to apply it to in this situation? The difference in sample means between, I did it again, I put 1 and 2 here. We are applying that notion of a standard deviation to the difference in sample means between calculus and statistics AP test scores. So our interpretation should say something like this. We start it the same way as we did for this parameter. For all possible random samples of 100 AP Calc BC scores and 50 AP Stat scores, okay, the differences in the sample mean scores for the two tests typically vary from the population mean score difference of 0.92 points by approximately 0.241 points. Okay, as long as you understand what a standard deviation does, it tells you by how much individuals in a data set typically vary from the mean. And then you know what random variable you're applying that to, the difference between two sample means, it becomes a lot easier to construct this. And again, you can copy this verbatim, but this is not the only way that you can write this. As long as you explain what the sampling distribution is of, sample mean differences between those two test scores, and explain what the standard deviation is doing, how much those values typically vary from the population mean difference, you're in good shape. Okay? It can look a lot different than this and still be perfectly right. But there are some things that you still have to make sure you include. The sample sizes from each population are very important because if they are different, these values are different. This value is different. Part of the interpretation of this parameter depends on these sample sizes being those. So those sample sizes have to be in your interpretation. What the standard deviation does, how much they typically vary from the mean. And in this case, the mean is the population mean difference in those sample means. Okay? So all of that would have to go into your interpretation there. You may not be asked to interpret these parameters. You may not have to craft these responses. But that doesn't mean you shouldn't know what they represent. Because again, the idea of what these things mean, more than just what their numbers are, is going to be important for what we want to do later on in the course. Let's close this video and this unit out in style by using what we've already learned in this video to answer a probability question. You knew we had to do it. What is the probability that x bar c minus x bar s is less than 0.5? Interpret your answer. Okay, so I don't think you would be given the question in this format on a real AP test. They'd probably just make it in words in the context of the problem. So writing it this way actually makes the beginning of the problem easier, but it makes the end more difficult. It's nice because we already have our probability statement. Remember, that's always what we want to write first. Okay. The reason it's important to write this statement before you do anything else, it tells you what the random variable for the problem is. In this problem, the random variable is the difference between two sample means. So, obviously, since in this video we've been talking about the sampling distribution for the difference in sample means, you knew that was going to be the random variable. But this confirms it. So the first thing you would do is check conditions to make sure you can use the model you want. I'm not going to belabor the point of what those conditions are. I wrote them here. We've already checked that all of these are met for this particular example already earlier in the video. Make sure you check those conditions first after you write your condition or your probability statement. Once all those conditions are met, you can actually write what the model is for this sampling distribution. So we know that the sampling distribution for the difference of those sample means is normal in shape. That's what this condition allows us to use. It's normal in shape, and we already, again, covered what the parameters are for this particular example. You would use the formulas that we talked about. We know that the mean is 0.92, and the standard deviation is 0.241. So this is the model we're going to use. And I'll tell you, getting from here to the answer of what this probability is very simple. Because you've done problems like this all year so far. You're just using a normal model. And you're trying to find the probability that it's less than some number. The fact that it's a sampling distribution, you can forget about that for right now. We'll get back to that when we have to interpret our answer. For now, we know that this random variable has a normal model, and we want to find the probability that the random variable is less than 0.5. Draw your curve. This curve has a mean at 0.92. The value we're interested in is 0.5. That's going to be somewhere to the left. And we want the area to the left. Okay. From our sketch, we know that this number should be less than 0.5 for the area, because it's less than half of the curve. Right? To find areas under the normal curve, we use normal CDF, as always. So here are your arguments for normal CDF. Our lower is going to be negative 9999, because we're going all the way to the left. The uppermost value in our shaded area, it goes up to 0.5. The mean of our distribution is 0.92. The standard deviation is 0.241. You may remember from way earlier in the course when we first introduced normal CDF, we usually found the z-score for this value first. You can still do that. It's not necessary, right? You could find the z-score that 0.5 represents and then use normal CDF going from negative 9999 to that z-score with a mean of 0 and a standard deviation of 1. That would be equivalent to this. And you can check and make sure that that's the case. You would get the same answer. Turns out this is equal to 0.0407. 0.0407. Okay. So, just to recap, probability statement first. Check the conditions that you need for this random variable so that you know what model you can use. Cite the shape and the parameters. If it's normal, draw your curve. Write out what you need to put into normal CDF. Calculate your probability. The only thing left to do is interpret our answer. And this is going to require some heavy lifting because we can't copy any language from the problem because it doesn't have any language as to what those things represent. So, you can pause the video and give it your best shot as to how you're going to interpret this 0.0407. Or I suppose you could just wait until I tell you what it means. But I think it's more valuable if you try first. Here's my interpretation. And once again, I want to make sure you know the interpretation does not have to say this exactly. As long as you interpret what the probability of this being less than 0.5 is, it can look different than this and still be correct. Let's go through it. It starts the same way as I interpreted the parameters of the sampling distribution for all possible samples of 100 AP Calculus BC scores and 50 AP Statistics scores. Now, we interpret what does this statement mean? Well, it's the probability that the sample mean calculus score is less than 0.5 points greater than the sample mean statistics score. Okay. Do you buy that? I'm essentially interpreting this inequality. That is the calculus score, the sample mean calculus score being less than 0.5 points greater than the sample mean statistics score. And that probability is approximately 4.07%. Not particularly likely. This jives with our sketch here. That should be a fairly small probability. Does that make sense? Well, the true difference in the populations is 0.92. So the average sample mean for calculus is going to be almost a full point bigger than it is for stats. But we're asking, what's the probability that that difference is less than 0.5? It's not going to be too many samples because the typical sample mean difference is almost 1. Okay, so not very often. If this had been 0, what's the probability that the calculus score is smaller than the sample mean statistics score? This number would be even smaller. It might be very, very close to 0, actually. But that's beyond the scope of what we're doing here. So, this is the end of Unit 5. I want to say that the information here is technically in Chapter 23 of our textbook, but we have just barely scratched the surface of that chapter. Don't read the whole chapter. Okay, we're just setting stuff up here. We'll get to that chapter later on in the course. But anything that's due for Unit 5 is probably going to be due very soon. Progress checks, Chapter 17 homework. If it's not due already, it will be very soon. Check Canvas for those due dates. You will have a progress check review video. As long as people do the progress checks, I'll make a video of the things that people missed the most, so you can review those. Look through the rubric of the free response questions. Either watch the video that I make, or once you've submitted it and I've graded it, look at the rubrics. See how your answer compares to the answer that gets the highest point total. See what you're missing. See what you put in that maybe you don't need. Okay, that's how you get better. It's how you get better. You have to look at what you're doing. You have to compare. So, do those things, the homework, the progress checks. If you do all that, you will be prepared for the unit test, and you will do well on it. Right? So, this will be the last new material for the semester. Going forward, I'm going to do some review problems. I'm going to assign them to you, and then I will review them just like they're a progress check. They'll be worth a lot of points. Check Canvas for details of that in the next few days. But worry about the Unit 5 test first. If you have any questions, as always, feel free to email me, and we'll make sure you get squared away. Until then, we'll see you next time. Take care.